Computational methods are used to study all types of conflict, including armed violence such as terrorism and different types of social protests. Academics and analysts at think tanks, government, and elsewhere comprise a broad set of researchers that benefit from these methods. One example project is the Early Warning Project by the U.S. Holocaust Memorial Museum. This project uses computational methods to forecast mass atrocities, including genocide. The U.S. State Department then uses those forecasts to inform the Global Fragility Strategy, which is intended to support U.S. government policies for countries experiencing or at risk of experiencing political instability and state failure. While studying conflicts, researchers face many challenges. One set of challenges relates to modeling. For example, conflict events are relatively rare, and relationships in the data are often nonlinear and endogenous. As a result, researchers have a large number of options when it comes to things like feature selection and engineering and choice of learning algorithm. Two, conflict is a social concept, and attempts to quantify it use very different conceptual and operational criteria, leading to multiple datasets on similar topics. For example, we don't have one dataset on civil wars, we have many. Analyzing different measures is a fundamental component of sensitivity analysis and leads to more robust findings. 3. We analyze conflict at different spatial and temporal levels, and use data in a variety of levels to do so. This presents challenges for joining and aggregation, particularly when the starting point is event data, which is common for conflict studies. Events are often associated with geographic coordinates and short time periods, and therefore present nearly unlimited possibilities for aggregating along spatial and temporal dimensions. Finally, while the abundance of data fosters more robust analyses, finding data resources that are relevant to a given question is not trivial. Political violence, instability, and social protest are complex issues with no simple explanation, and as the number of potential explanations for these events expands along with more data available, researchers are left with the task of sorting through large quantities of information to identify what is meaningful for their problem. To address these challenges, we propose an ecosystem of tools for conflict data management and usability, predictive modeling, novelty detection, and visualization. The goal is to facilitate the study of all types of conflicts by domain experts, helping to carry out complex computational workflows and streamlining data exploration and discovery. The ecosystem allows for exploratory visual analysis and model building, generation of insights and assessment of hypotheses, identification and processing of relevant data resources, pruning of useless information, and the construction of machine learning models. We also provide a number of features for exploring different solutions from automated machine learning, so analysts can develop insights into their models and features. One focal point of our integrations is handling multiple datasets that an analyst might bring to bear on a particular problem. We do not make assumptions about the relevance of any dataset and see streamlined access to multiple datasets for a single problem as one important contribution and also an area for future research. There are existing tools for addressing these challenges in modeling political violence. R and Python are commonly used, but require considerable expertise for analysts to complete the full range of common tasks. Furthermore, even with expertise, programming takes time. There are many tasks, particularly related to spatio-temporal data, that are easily facilitated through integrations. Customized visualization tools are very effective for exploration of a specific dataset, which is the intended purpose, but do not accommodate the wide range of tasks that analysts need. Other interactive tools can be quite effective for data exploration with little programming expertise, but are not domain specific, so lack emphasis on spatio-temporal data and machine learning. The common workflows that analysts employ require more than what is provided with tools like Tableau and Microsoft's Power BI. Our ecosystem is intended to accommodate a broad range of tasks which domain experts can carry out efficiently and without the requirement of programming expertise. Our ecosystem is composed of 4 components. Two Ravens is a web application for statistical analysis and data exploration. The interface allows researchers to explore data with visualizations, to specify models and configure machine learning problems, and to use automated machine learning to provide solutions that can be explored in a number of ways. In this brief demo, we can see a user shifting between Model, Explore, and Results mode. Different modes signify different main goals a user might be attempting in the current part of their analysis. For example, in Results mode, we assume the user has already specified the model and configured the problem, and is primarily interested in exploring and visualizing the solutions returned by the automated machine learning engine. Two Ravens is a very visual system. Researchers impart their substantive knowledge about their data and research questions in ways that are intuitive. The goal is to allow the domain experts to complete a high-quality, predictive, and interpretable model. Two Ravens for Event Data is designed to explore conflict events and to transform the data into usable time series formats. Researchers may subset by spatial, temporal, and other attributes such as event type. Here, we can see the actor grouping feature highlighted. Al-Shabaab is a violent extremist organization based in Somalia, and the U.S. State Department has designated Al-Hidra as a wing of Al-Shabaab. Events associated with either actor are grouped into a single entity, here named simply Al-Shabaab. After selection, users may aggregate to an appropriate level of analysis to view the time series or export the data. Here, we aggregate counts of explosions or remote violence to the monthly level and can view Al-Shabaab's use of this type of violence over the selected time period. Octus is a dataset search engine that helps users find relevant data for their machine learning models and data analytics tasks. Similar to a search engine like Google, users can pose keyword-based search queries, and Octus then retrieves and ranks the most relevant datasets from its index. Octus also supports a rich set of data discovery queries. Besides keywords, users can also explore dataset collections at different spatiotemporal levels and submit their own datasets as input to search for datasets that can be integrated to them through their either join or union operations. This last functionality is important in the context of conflict studies because researchers increasingly use machine learning to forecast conflict, but often need to find additional relevant datasets that can be integrated to what they already have in order to build better models. Finally, PODS is a tool that, given temporal datasets, derives explanations for outliers that occur closely in time by identifying meaningful relationships between them. It proposes a statistical criterion to determine whether outlier relationships are meaningful, and it does so by verifying if such relationships could have been predicted from non-outliers. In other words, PODS checks for the existence of a statistically meaningful trend across aligned non-outliers that becomes stronger as it approaches the aligned outliers. Since conflicts often materialize as outlying values in datasets, such as abnormal peaks in the monthly number of violent events, having an automatic mechanism to discriminate data noise from outliers that correspond to events is desirable, especially when the analysis involves a large number of datasets and the manual outlier inspection becomes infeasible. With a high level of compatibility between components' inputs and outputs, our ecosystem allows for integration across its tools with little to no programming effort. Our ecosystem takes the spatiotemporal character of conflict datasets into account, which is generally a challenge for data management. Users do not need to spend time converting data or implementing scripts to use different tools in a combined fashion. As mentioned earlier, it's often important for analysts to access and analyze multiple distinct datasets for a single problem, which our integrations facilitate. For example, using Octus, it is possible to search for new datasets within a geographic region or a particular time period. Or, if the researcher already has multiple relevant datasets, each could be uploaded to Octus, where they'll be profiled and prepared for joining. Political event data may also be explored and prepared for analysis with Two Ravens for event data. Either of these two systems, Octus or Two Ravens for event data, can feed new data into Two Ravens for further analysis. With the multiple new data sources, a researcher might use PODS for novelty detection, leading to a refined or new hypotheses. Different prediction problems could be solved with our integrated automated machine learning engines, and solutions can be explored. Overall, workflows are nonlinear and iterative, and discovery is important, so the system must be flexible. As a result of these integrations and the flexibility they afford, the total of our ecosystem is greater than the sum of its parts. One case study highlights the integration of 2Ravens and Octus to improve predictive modeling. In this case, the researcher has a dataset to forecast subnational violence in 7 West African countries: Benin, Burkina Faso, Cameroon, Chad, Mali, Niger, and Nigeria. 2Ravens has a component to automate machine learning problems that might be of interest. Here, we'll just select the one designed to forecast political violence. At this point, the analyst can begin to specify the model and configure the machine learning problem. This includes things such as selecting predictors, providing information about spatial and temporal dimensions, and choosing to solve the machine learning problem as a regression task as opposed to a forecasting task. However, a researcher may notice that the data lacks information on social unrest, which might be expected to contribute to the use of armed violence. If the researcher knows relevant data was in 2Ravens for event data, she could transition there and begin to explore it. Or, if she possessed the dataset, she could upload the data to Octus and take advantage of the built-in data profiling features for spatiotemporal events. Alternatively, she might just search Octus to see if anything in the repository is relevant, for example, by searching with the keyword protest. So, from 2Ravens, she opts to augment the data and queries Octus with the keyword protest. Octus retrieves the social conflict analysis database, which she selects to join with her data. She'll choose the attributes to join on, as well as the method for aggregation. Here, this is simply a count of the number of events captured by the social conflict analysis database. Transitioning back to 2Ravens, the new feature to capture social unrest has been added to her workspace and can be included as a predictor. She may wish to solve the problem with and without this particular feature to begin to assess the hypothesis about the role of social unrest in forecasting political violence. The automated machine learning backend can provide a number of solutions to the forecasting problem. Solutions are scored according to the chosen prediction metric, and these scores may be compared. The system has a number of other features to explore the results, including predictive versus actual plots, maps and visualizations to understand predictions, and measures of variable importance and interpretations. At any point, a researcher may transition from results mode back to model mode to specify a new problem, or even go back to Octus or event data to find new resources useful for this particular problem. The ecosystem of tools we presented helps domain experts in conflict research. The tools are easy to integrate and facilitate the formulation and refinement of research hypotheses. This ecosystem also provides benefits to data scientists that typically work with domain experts to realize the value of computational methods. Thus, we expect that systems such as ours will have a multiplicative effect on research output. Open data management questions that can be explored in future research include how to implement mixed initiative visual interfaces that allow users to explore their needs in more detail, how to aggregate data from the event level into grid-based or other spatial and temporal units, better addressing the spatiotemporal complexities of conflict data, and how to use natural language processing techniques to better make sense of domain experts' information needs.